we just got done figuring out how to make a phase line from a slope field, but it turns out we don't need the slope field. You don't have a slope field, no problem. Just figure out where those equilibrium solutions are, and then let that kind of define your test regions. You set up some intervals. And so just as a reminder, what we're going to be doing here, the process is we got to find and label the equilibrium solutions. We have to draw the arrows around the equilibrium solutions, and then classify the equilibrium solutions. So those are the three main steps, right? We draw our line and then we do that. So for this first one, we've got our first example, we've got our differential equation. I'm just going to go ahead and draw the line. Now I'm not going to put arrows on either end, right? I know there's going to be some equilibrium points in here, but I don't know what they are yet. So off to the side, I say, okay, so where is this thing equal to 0? Where are the equilibrium solutions? And I can figure those out by saying, where is the derivative equal to 0? And it turns out there's two. One of them happens to be at y equals 1, and one of them happens to be at y equals 0. So we'll call this one y1 and y2, and that one y2, right? So we can go ahead and label those on our line right now. So I'll just make this right here. I'll call that y1 equals 1, and this one down here, I'll call that y2 equals 0. Right? And of course it makes sense that they would be in this orientation. 0 is going to be below 1. Now the only question is, what direction do I draw arrows in those three spots? So I have to set up a little bit of a test interval. So use test values. And in order to do that, I'm going to say what my test value is and what my sign would be. The sign of dy dt. And so if you keep in mind my two known equilibrium solutions are 0 and 1, I need something that's kind of above 1, something that's between these two, and something that's below 0. So I'm going to go with something like y equals 2, y equals 1/2, and y equals, I don't know, -1. And so if I plug in 2 into my differential equation, you can see 1 minus 2, that would be a negative times a positive. So it would be a negative times a positive, which turns out to be a negative, which means that in the region above y equals 1, it's going to be a downward arrow because it's a negative slope. In the region between those two equilibrium values, if I plug in a value of 1/2 into my equation, I'd have a positive times a positive, which is going to be positive, which means that the sign of my derivative in this region is everywhere positive. So that means an up arrow in between there. And of course, y equals -1 is below this, so it's going to represent everything below that equilibrium solution. And so if I plug in -1 here, I get 1 minus a -1, which is a plus, and then negative out here, which is going to be a negative overall. And so that means I'd have a downward arrow there. And then the last step in this process is to classify each one of these things, each one of these equilibrium solutions. And this one, it looks like everything's going towards it, so I'd call that a sink. And this one, everything's going away from it, so I'd call it a source. So that's one example of how we could draw a phase line. Let's see another one. This one's a little bit more interesting because, well, as you'll see, this example has a whole bunch of possible equilibrium solutions. So let's figure out what they are. So for starters, I'm going to take a look at my equilibrium solutions. And if you're paying attention here, you might discover there's one right here at w equals 0. And then everywhere that cosine itself is equal to 0. So there's an infinite number of them. As a matter of fact, they look like pi over 2 and negative pi over 2, 3 pi over 2 and negative 3 pi over 2, 5 pi over 2 and negative 5 pi over 2. So plus or minus, plus or minus, plus or minus. So you can see there's going to be an infinite number of these things. So that means we can't draw them all. Which means we're going to have to look for a pattern and see if we can spot a pattern in order to help us understand what's going on the phase line. But we can still set up some test intervals. So let's test. And so our intervals are going to need to be right around 0, but smaller in size than pi over 2. Okay, so our W values that we're going to test, the first one might be something like pi over 4 and negative pi over 4. Those are on either side of 0, but yet not as big as pi over 2. And then, of course, we need something between pi over 2 and 3 pi over 2. So plus or minus pi would work for that. And then we need something between 3 pi over 2 and 5 pi over 2. So plus or minus, I don't know, 7/4 pi or something like that. That ought to work. And so all I'm going to do over here is write the sine of dw dt. And so for the first couple, we'll go ahead and fill these in. The first couple are pretty easy. Pi over 4, cosine of pi over 4 is positive, and pi over 4 itself is positive. So that would be a positive times a positive, which means it's positive. For negative pi over 4, if we plug it into our original differential equation, it would be negative here, but cosine of negative pi over 4 is positive. So it's going to be negative times a positive, which gives me negative. And so if we do the same thing for pi, then we wind up with positive times a negative, right? Positive pi times cosine of pi is negative 1. And so if we do this again, we'll have a negative times a negative, which gives me a positive. So that'll get us started. We can do some more here in a second, but let's get started with the phase line and see what we can draw. So off to the side, we're going to draw a phase line, and smack dab in the middle, we'll go ahead and put our W equals 0. And you can call it W1 and W2 and all this stuff, but for our purposes, we're just going to kind of identify these locations. So if we take a look at the next one above that, the next equilibrium solution is pi over 2. And the next one below is pi over 2, but in the negative side of things. And we know that between 0 and pi over 2, it's positive. That's what we get from right here. And between 0 and negative pi over 2, it's negative. So already we can see that we're talking about, in our phase line, W equals 0, that's going to be a source. But now we go one more out, and we say, what about 3 pi over 2? So 3 pi over 2 is going to be up here. And negative 3 pi over 2 is down here. And so in between pi over 2 and 3 pi over 2, on the positive side, we have a negative. So it's going down like this. And between negative pi over 2 and negative 3 pi over 2, we have a positive. So our first one, W equals 0, was a source, but as we look above, the next equilibrium solution is pretty clearly a sink. And the one below it, below 0, is also a sink. So we got to go one more beyond to be able to get a sense of what's going on here. So that means we need to look for 2 more test values. And these 2 test values that we're going to look for are going to be between 3 pi over 2, 270 degrees if you want to think of it that way, and 5 pi over 2, which is 1 full circle and then a half a pi. So the most obvious answer between them is 2 pi and negative 2 pi. But do you see the problem with using 2 pi and negative 2 pi? If I plug in 2 pi for cosine, what's the cosine of 2 pi? Well, that's just the same thing as the cosine of 0, so that's a positive. So we'd have a positive times a positive, which is a positive. And with negative 2 pi, if we go whoop all the way around, it's still positive. But it's positive, oh sorry, positive on the outside because that's negative 2 pi times, that's the first part, negative 2 pi times, this would be a positive value. So negative times a positive is negative. So if we go out these two equilibrium solutions, we go one more after this, and we're going to see what happens. We would have on the upside of things, that would be positive, so they're going to be going an up arrow there, and then down here it's negative, so a down arrow there. Now, there's more equilibrium solutions after this, but I think you can probably see what the pattern is going to result in. This is a source, this is a sink, or sorry, this is a source. And guess what the next one's going to be? It's going to be a sink, and then the one after that is going to be a source. And so we can see that in both directions, the pattern continues. So a switching back and forth between source and a sink, and a source and a sink, and a source and a sink. But it all started off in the middle. The middle is a source, and then above and below it is a sink, and then above and below that is a source. And so what we should be able to do is hop on Maple and verify this by taking a look at the slope fields for not only this example, but the example above. So let's take a second. I'm going to pull up Maple, and we're going to see whether or not our phase line looks like what we expect based on the slope field. So here we are in Maple taking a look at the slope fields for the two problems that we just got done making a phase line for. In the first example, we have our 1 minus y times y, and you can see there's two equilibrium solutions. I identified them over here with the initial conditions, and you can see above we've got negative turns to positive slope, turns to negative slope, just like we predicted. So this guy right here is definitely a sink. This guy right here is definitely a source. And the cosine times, or cosine of w times w problem, I didn't draw all of the, equilibrium solutions, but I gave us a view of right around w equals 0. Excuse me. So we can see w equals 0, w equals pi over 2, w equals negative pi over 2, and I put in w of 0 equals 3 pi over 2 and negative 3 pi over 2, but I don't think I gave myself enough room here. So let me go up to 5 and negative 5 for w. And there we are. There you can see them. Whoops. You can see my solutions, my equilibrium solutions. And just as the phase line would predict, we start off in the middle with what appears to be a source, and then above and below that is a sink, and then above and below those are sources, and we can verify the pattern continues. If I were to stretch this out even further, go out to like 10 to negative 10 in the vertical direction, we would see a series of alternating sources and sinks. So source becomes sink, becomes source, becomes sink. And so that's exactly what we predicted with our phase line. So switching back over to the document, these two were exactly as we predicted. So we're going to take a look at one more example in this video. It's on the next page, on page 50. And this particular example is a little bit more friendly, of course, because it's a nice quadratic. And so we're going to follow our same procedure as before and figure out what the equilibrium solutions are. And so we figure out the equilibrium solutions. And in order to do that, we have to set that polynomial equal to 0. And a little bit of factoring goes a long way. This becomes y minus 7 times y plus 1. And that means there's two equilibrium solutions expected, one of them at y equals 7, the other at y equals negative 1. So we'll call this one 1, we'll call this one 2. And so off to the side we can draw our line that's going to represent our phase line, and we can plot those 2 points. This is going to be y1 equals 7, it's above, and y2 equals negative 1 is going to be below it. Now the question is, what direction do we draw those arrows? Well, if you recognize this is a polynomial, this is a quadratic, and those are the two roots, this thing is going to be an upward facing parabola, which means that on the ends it's going to be positive. In between, it's going to dip down and become negative. But we can test it just to be sure. So if we set up our test values, we can say the y values, and then what's the sign of dy dt. And so a y value that's above the largest one, so let's try it with y equals 8. And then in between would be something, let's go easy, let's make it y equals 0. And then below y equals negative 1, y equals negative 2. Why make it hard on ourselves? So if we plug in 8, remember, we don't care about what the value is, we just care about the sign. So 8 in this would be 8 minus 7, so that's positive. This would be positive. It's a positive times a positive, which is going to be a positive slope in that region. So off to the side above, I know it's going to be a positive slope. In between, if I let y equals 0, then I'd have a negative times a positive. And that's telling me I've got a slope downward in the middle. And last but not least, if I throw in a negative 2, I'd have a negative times a negative, which is positive. And so we have our phase line drawn. The last thing that we need to do is figure out how would we classify these. And for this one, you can see, oh, that's going to be a source because they're both going away. This is going to be a sink. And that is the phase line. Now, what I was mentioning before, I can show you on Maple here. So give me a second. Let me pull that up. So here we are in Maple, taking a look at the phase, or not the phase, the slope field for that differential equation, y squared minus 6y plus or minus 7, and you can see it predicts two equilibrium solutions and the orientation of those slopes just as we predicted. But what I want to show you here is that we could, if we wanted to, plot the right-hand side of the equation. I'm just going to write it as in terms of y. So it's going to be y squared minus 6y minus 7. And I'm going to plot this on a set of axes, but the horizontal axis now is the y-axis. So y is going to go from, I need it to go as far down as negative 1 and as far up as positive 7. So I'm going to go from negative 5 to 10 just for giggles. And let's see what we get. We get a plot that looks like this. It's that quadratic that we expected. And the places where this quadratic touches the y-axis on this graph are the places where in the vertical direction the slope, which is what the vertical axis for this graph would be, the slope is equal to 0. So what you're seeing in this graph is really the same information as this slope field. It's just giving it to you in a different way. Everywhere above y equals 7 has positive slopes. Up here, that's what we're seeing over here. Everywhere above y equals 7 has above the axis, so positive slope values here. Because what we're really doing is we're plotting, I'm going to give it a title here. This is the plot of dy dt versus y. So the horizontal axis is y in this case. So everywhere in between our equilibrium solutions had a negative slope, and we see that here between the equilibrium solutions has a negative slope. So this graph, this plot of the function dy dt, is another way we can represent the information about an autonomous differential equation. It comes in really handy. So we're going to end by taking a look at, switching back over to the document and saying at the bottom, if you look at the point at y equals -1, all solutions flow into it. That's what we call a sink. The one at y equals 7 is what we call a source, because everything kind of seems to flow out of it as t approaches infinity. And then a sink, if it's not a sink or a source, we call it a node. This is just referring back to the information that we had before. So what you're going to do, there are 3 examples that remain in this section on pages 51, 52, and 53. And you are going to follow the instructions and create the slope or the phase line for each one of them. Or in the case of the last one, you're going to start with a phase line and work backwards to what the slope field and maybe the graph of f of y must look like. So give those a try, and I'll post the solutions to those on our notes page.